Thanks, Nina. Oh, sorry, it was off stage when the applause went off. So our next presenter is the organizer of the Peninsula Meetup, and is today going to be talking about exploration-oriented programming. Please welcome Moshe Zadka.
Hi, everybody. I'm going to talk to you about exploration-oriented programming, but first I want to talk to you a little bit about my childhood. This will be relevant in a minute, I promise. So this was the first time I programmed a computer, a close approximation. This was Logo. I booted up the environment. I could tell the cursor to go forward. I could tell it to the left. I could tell it to go forward, make a little nice corner. And I could even write functions. I could run the functions. It would roll a little bit more. I could even change the functions and run them again, and it would roll a little bit more. And it was a lot of fun. I liked programming. Then I got my own computer. This is around when I was 7. And I had this. Right? This is basic. This was really fun. I could write programs. I could run them. I could change them, run them again. They would print stuff. It was a lot of fun. And then I learned that this is not the way proper programming is done. Proper programming is writing reams of code into Turbo C++, and then it fails to compile. Then you fix it, it fails to compile again. And then after this hour you spend trying to get it to compile, you run it, it crashes. Then you fix it, it doesn't compile, and so on, and eventually it kind of runs. And this was proper programming, and that was really boring, and I said I hate programming. This is true. This is all the way until I was 20, so we kind of skipped a bit. And I saw this. And I could write functions, and I could run them, and I could change them, and I could run them again. And programming suddenly seemed like fun, so for some reason it was really, really hard on my up arrow. Because you write for loop, and you make a mistake, then you write up arrow, enter, up arrow. And as much as modern keyboards are pretty reliable, that was a lot of stress on my up arrow. So eventually I got tired of that. And then this came along. This is IPython. This is pretty awesome. Yeah, you can cheer for that. That's awesome. I really enjoyed it, right? Because now my up arrow wasn't getting as much use, right? I could up arrow, and I could fix the for loop. I put in parens, and now the for loop runs. My IPython did not have parens on print, because this was a long time ago, but this is modern IPython. And suddenly programming was fun again, except it didn't have pictures, like the logo and basic stuff. Till this came along. Jupyter, ACM award winner for this year, I think. And now you can have pictures, and you can have functions, and you can run them, and you can see what's going on, and then you can fix the functions, and you can see what's going on. You can define variables, and run them again, and play with it, and until you see that your code looks great. And this was fun, and now I like programming again. And I want more people to like programming. So I'm going to kind of tell you a little bit about Jupyter, how to use it to make your life better. So I feel like there's levels of how deep you get into Jupyter. You can start exploring your code with Jupyter, right? Just importing some of your functions and playing around and seeing what's wrong and kind of using it as a debugging aid. And this is great, right? This is not to be frowned upon. But I feel like the next level is when you actually use the notebooks as a collaboration mechanism. You share the notebooks with your friends, you show them what you did, or your colleagues, and they share them with you, and maybe you check them into source control, and you discuss this just as you would a normal pull request. And then the next level is when you treat your notebooks as an artifact to be tested, right? You really treat them seriously. They have to be correct, right? Sure, when you're playing around with them, just like when you're playing around with your code, it's not correct, but once you check it in, you expect it to be correct. Maybe it's not correct in the PR, CI tells you what's wrong, you can fix it. And finally, and this is a step I have not gotten into, but this is kind of my aspiration, and part of my goal for writing this talk is to figure out, how can we actually make this so that we don't, in the end, have to copy-paste bits of our notebooks into production? How can we actually use notebooks in production? So this is kind of the aspirational. I don't know anyone who has managed to get there, but this is kind of my goal with Jupyter, and I want to leave you with a sense of the future at the end of the talk, so I will kind of go through these levels more or less in order. So if you've never used Jupyter before, it is pretty awesome. So when you run it, it's made of a web interface. that I kind of showed you a screenshot of. That's what you write your Python snippets into, and you see the output, maybe in graphical form, maybe in textual form. Behind the scenes, it runs a kernel that actually interprets your Python. It keeps a persistent history, and it also has a bunch of other goodies. Some of them I might get to, and some of them I probably won't get to, but it is pretty nifty, and you should look at the other goodies if you're actually using Jupyter. So what does the kernel do? The kernel is basically a variant of IPython that sits in a loop. It handles snippets, mostly of Python. It interprets them, but it is just a regular Python process. So like any regular Python process, it has an in-memory state. So if you tell it to open a file, it will keep the file open. If you tell it that the variable is equal to 15, it will remember that this variable x is equal to 15. If you read something from the file, or you ask it to multiply x by 2, it will read something from the open file and return it to you, or it will return to you 30. And in general, in normal Jupyter workflow, we treat the kernel as semi-disposable. And both of these parts of the word is important. It's not completely disposable, right? It runs for a long time. Like some of my kernels on my laptop, on my work laptop, are running for like days at a time because they keep like interesting state, and I don't want to lose this state. But at the end of the day, it's very, very easy. And this is, like, in some sense, an advancement from, like, the environment you saw of me using as a kid. It's really easy to say, throw away all in-memory state. I want to start from a clean slate. And this is really useful, right? You've done a bunch of things, and you have no idea where you are. Restart it. I don't want any of these open files. There's probably, like, a gazillion of them, and they're all open to different files, and that's bad. So it's very easy to throw away everything and start from a fresh kernel. So it's not fully disposable, but it's not fully non-disposable. IPython, and by extension, the Jupyter Python kernel, which is almost a variant of IPython. Internally, they share almost all the code, can handle so-called magic, which is not Python. Python does not have %% That would be a syntax error in Python. So you can send it a bunch of magic commands that are more for the kind of interpreting stuff on the line, right? Like PDB, obviously, if you want to launch a new debugger, or you can change how it captures output. And that's very, very useful. And like the magic list in IPython, if you've not used IPython or Jupyter before, you owe it to yourself when you start using them. If you do use them and you haven't seen the magic, you definitely owe it to yourself. Just like look at the magic list. There's a lot of functionality there that is useful. And you can actually add new magics, which is also pretty cool. So one Jupyter server can run many kernels. And the reason that's very useful is because, for example, we at work, we're using a microservice architecture. Every single microservice is its own Python project. It has its own requirements, and we don't want to cross-contaminate dependencies, right? One thing has a dependency on like a weird version of TensorFlow. I definitely don't want to infect all the other things. So your Jupyter server can run a kernel per virtual environment. And unfortunately, if you do everything the right way, meaning, of course, you install Jupyter in its own virtual environment, and you launch that, and then you launch every kernel in its own virtual environment. Exactly how to bind everything together is not obvious. If you read the documentation, you kind of have to interpolate quite a bit. I've done that interpolation for you. And it's not easy, but it's not hard. I don't expect any of you to like actually read all of it, but it is easy enough to shove it with a little bit of a hammer into one slide of a talk. So, you know, like it's kind of subtle. There's like a multi-step process of like building the configuration and installing that. But once you get it working once, right, this is computers. Once you get it into any place, these slides will be up. You don't have to take pictures and then use OCR. They will be up as a textual resource. So once you do that, then you can have a lot of kernels in your Jupyter. So you have one kernel for your front-end service, and one part for like, you know, whatever uses a queue. And you know, if you have a different microservice environment, you can have one kernel for each one. And each one, you can import the code for that microservice and maybe add to that code from that kernel. So that's pretty nifty. And too few people do that. And I think that's because the process is a little bit subtle. it's a web server, and like everything in the web, I'm contractually obligated to talk a little bit about security because it is literally a remote execution engine. That is like its entire job, right, to remotely execute whatever you do. If you didn't do that, it would be a very poor interpreter. So how does it work so that like not everybody can do that? So by default, it listens only on local hosts. You can get it to listen on non-local hosts, and that's very important if you have interesting environments. And like interesting is kind of captures a large swath. Maybe you want to run your Jupyter on an EC2 machine because you're running on a Chromebook and it's very weak. Or maybe you're running on a Mac, but most of your interesting stuff is on Linux, so you want to run it inside of a Linux VM. Or you have some complicated setup with Docker and Docker machine involved at some layer of that, like I always happen to have. So you can actually force it to listen on non-local host. And that's where the second security mechanism comes in very importantly. It uses an opaque security token. So when it starts up, it will literally write that token to the standard output, so you can copy-paste it to wherever you need to. And if the auction make like a kind of an honest attempt to launch your browser with a link to that so that it auto-launches. So if you're a normal person and you just run Jupyter, it will just spin up a browser tab. But of course, again, if you have an interesting environment, and again, interesting covers, even a larger swath here, maybe your default browser is configured incorrectly, like it is on my personal machine right now, or for whatever reason, then you can just go to the Jupyter server manually and put in the token, and from that point on, it cookies your browser, and your browser is good to go. So you don't need to do it if you restart your browser, unless you restart your server. So once you're in Jupyter, you're going to be using a notebook. A notebook with editable history. And again, both parts of the words of that sentence is important. It's a history. It shows you what you've done, but you can go back in time and change the definition of a function. If you've seen the talk that was going around, that was like the counterpoint to my talk, which is like, don't use Jupyter. He made a big deal of like, you know, that's a problem. I don't think it's a problem. I like being able to edit history because I make mistakes, and I like to go back and fix them. So when I put my notebook out for people to see, they don't have to go through my mistakes. This does mean that you can cheat with a notebook. So a notebook is not proof that you have done what you've done. It's a way for other people to reproduce your work, right? This is why I think it's so important for data science. It is not proof that your work is actually there. I don't see the use in like a proof thing, right? Like anyway, like it's not cryptographically signed or anything. It is a way to share, so it is on you to make sure that after you're all done, you can, again, start with a clean kernel and make sure that your history works, but you can go back and edit any part of the history you need so that you can get it to be better, right? If you made a mistake, that's okay. You fix it, right? It contains the inputs and the outputs. So if you save your notebook and you give it to your friends, they do see the results you've seen. Again, this is not a way of proving, but this is a way of communicating, right? Like, even like, you know, in normal communication, we do not try to prove things to each other, but we do try to convey information, hopefully in a trustworthy way. So you can communicate the outputs to your friends and colleagues. And it does contain only code. It does not contain the in-memory state. If you restart the kernel, all the open file objects are gone, right? This is not like a magic pickle thing. It's very good. You do not want a magic pickle thing, but it is important to remember that the notebook only has the code and the somewhat rendered versions of the output. It does not have all your in-memory state.
What's the checkpoint that it creates?
I'm actually not sure, and I never trust it. So I'm going to talk a little bit about like collaboration, but basically I believe in checking notebooks into Git, but I'm going to talk a little bit about it in the in my talk. When you write a notebook, remember that your namespace is global. If you define a variable and call it something, and like, you know, assign 15, and you multiply it by 2, you will get 30 in the next output, right? That's, you know, a feature, but it is a feature that comes with a price, and the price is global namespace. If you define a variable called a way in the top, and you forget about it, Jupyter has not forgotten about it. If you use a in a function and you haven't defined A, then it will use that A. Maybe when you define functions in a global namespace, just like you do when you write normal Python code, do not use super short names that are easy to mistake for variables in functions. Like, think about the names you give things. Right? This is, again, important, especially when you treat notebooks as something that you actually want to communicate with. You can redefine functions, because remember, in Python, defining a function is literally just an assignment operator. And like I said, you can assign anything. It's a global namespace. So I first assign foo to something that, that multiplies by 2. I see that multiplying by 2 is too little for me. I actually needed to make it go boom and actually multiply by 3. I multiply by 3. This is a very, maybe this is not the most common bug, but this is a very typical way of working, right? Like, you made a mistake when you define your function, and that the only way you noticed that you made a mistake when you defined your function was you ran your function, and it gave you not the output you were expecting. So you change your function, and then you run it again. And with numbers, it's pretty cool, right? Because we got 10, and then we run it again, and 10 is the same 10, right? But if you think about it with lists, it's going to be different, right? If you mutate a list, that list is mutated, right? You cannot go again and try it. So if your bug was that you accidentally deleted half the elements from the list that you did not have to delete, now you don't have the elements to rerun the function. This is why, in general, I think this is a better way of approaching code. I have another talk about why you should always use immutable data structure. You should always use immutable data structure, but in interactive programming, more than most, right? If I define A, and then I run increase head, now, in this time, increase head actually worked fine on the first attempt, right? It did actually increase the first element. But if it accidentally increased the second element by 1, I could fix it, and rerun it, and it doesn't change A, right? It just returns a new element. And this is using the persistent library, which I didn't bother actually importing because that would take more space. But the important thing is that this is O of log n. This is not O of n. It did not copy the whole list. The two lists share almost all the internal structure. So if this was not 3 elements, but say 1 million elements, you would not be taking up 2 million spaces. You would be taking up 1 million plus a little bit of overhead, like an extra 10 spaces for kind of internal arrangement. So if you use a lot of immutable structures, you can actually rerun your functions over and over again until you get the result you wanted. You can check if that's the result you wanted. You can see it. You can look at it and see that it does the right thing. So again, this was like 3 elements. So it was pretty easy for me to verify by eye that, like I only increased the first element and it didn't touch any of the last element, and also it was like a 2-line function, didn't have a bug in it. But imagine that it is a 50-line function that runs a complicated algorithm, and verifying by eye suddenly is like quite a bit harder. So you can use actual assertion libraries. My favorite, which again I did not bother to import because it would take more space on the slide, is PyHamcrest. And the reason I like PyHamcrest so much is because it's just an assertion library. It doesn't try to be a test runner. It doesn't try to be a test class, weird subclass that you need to subclass for. It has functions that you call. I really, really like libraries that have functions that I call instead of like needing to do a weird inheritance magic. So it has assert that, and it has the is function, and it can also assert very, very subtle things. I have more written on PyHamcrest in other places, so I'm not going to talk about it too much. But this is a way to verify that your functions actually worked correctly. Right, if the verification is not that simple, right? If you say want to make sure that the array at the end still has the same average because whatever permutation you did should not have changed the average. Now, some people also complain about how hard it is to implement classes because with class you have like one really, really big stanza that starts with class and then like it has like a lot of functions. And in general, I think that's a bad sign. And if that's the problem for you in Jupyter, that's probably like you're not writing very good Python. So obviously, you're going to use the attrs library to define classes. And again, you want to make them immutable. And once you make classes immutable, you suddenly realize that you need a lot less methods than you needed. Because a lot of the time, the reason you make something a method is to keep it invariants. But the invariants are always going to be kept if you created the class correctly. Because it's immutable. You cannot change it, so you cannot change any of its invariants. So that's fine. So you can make things functions. But you probably are thinking to yourself, Moshe, I want methods because methods are polymorphic, right? Like a point in 2D has a different absolute value than Trey's much more professional 3D point. So that's fine. You can use a single dispatch, which is a function in the functools module, to make polymorphic retroactive functions. And that's really nice because you can have polymorphism without changing that. And you'll notice that each one of these, I didn't just have the line around it for fun. This is actually, can each one of them be a different cell in Jupyter, which means if I make a mistake in the definition of this absolute value, say I want to switch to like linear absolute value, I can just mutate this cell and change the registration. That's it. I don't need to mutate anything else. So let's say I got the wrong thing because like, oh my God, this should have been the absolute value instead of the Pythagorean distance. I could just do that. And that's it. So now that you know how to write notebooks, I'm going to talk about collaboration a little bit. So on the inside, notebooks are JSON files, which sounds fun, right? Like, you know, because they're text files, and you're probably going to get halfway decent diffs, so you can just check them into Git and have people pull requests. Until you remember they have the output and a bunch of metadata about the output, like execution counts and like the literal output and something. And this will often cause diffs to be really big, right? Which if you're reviewing pull requests, the worst thing you have is extraneous parts of the diff, right? Because that makes it harder for you to see that what I really did was change the definition of the absolute value. So that's annoying. So you can clean the outputs. You can literally clean all the outputs and have people review the something cleaned. If you're actually going to do it in day-to-day life, what you can do is put a pre-commit hook that cleans all the notebooks. Now, these won't be valid notebooks. You're not going to be able to use them. But you can use it you can test in CI that the re-cleaning is just the same. And then you can, in the code review, you can only review the cleaned ones, and you'll only get the diff you need. So that's a lot of fun. You can even write a custom Git diff tool. This is pretty easy. I'm not going to go through the details of this, but difflib is pretty neat. And you can literally write like your own differ if you're doing diff locally. You can also write a custom merge. I don't think I can shove that into my into a slide, even if I like break every good rule of slide design. But I kind of try to kind of give a little bit of guidance, so you can actually do a custom merge. Now, at some point, you're going to care about the quality of your notebooks. You share them with your colleagues and friends. You want to make sure that they don't regress. Running Flake on a notebook is pretty easy because it literally has an internal Python converter, so you can run something like that in CI and make sure that you actually, again, like you don't need to do it while you're playing around, but before you actually merge into source control, you probably want the Flake to work. You can even write a test by just filtering out anything that you marked as interactive only. And then you can literally run it and make sure that you don't get exceptions, or run it with PyTest and have all the test functions that you've written with PyHamQuest that you've run in interactive only mode. So you can literally write something that will mutate into something that PyTest can eat and run the test from. Now, this will make sure that notebooks are correct, but this still won't have you running stuff directly from notebooks in production. This is aspirational. I've never seen anyone do that, but I'm super interested to try it, and I'm super interested to work with anyone who wants to try it. So you literally can write like a notebook loader. Again, I won't go into the details here, but Python's import infrastructure is really, really flexible. You can do pretty much whatever you want. So for example, you can go cell by cell and literally just execute them in the context of the module. And then you probably need to write a notebook finder because of some details. It is very flexible, but kind of annoying to actually put in production. And in this case, I'm cheating and by not allowing notebooks to be top-level modules. You probably want that. You probably want to put your notebooks in a package. And you can literally do that by just making sure that in your init, you add the notebook loader to your meta path, to the path of the loaders. You can even produce documentation by doing something like that, and because things depend on importing, we've already dealt with import machinery, we'll just reuse that work. So that will give us the API reference. And we can also get the prose reference if we export all the markdown parts. So we can actually generate documentation and put it in some CI that produces documentation. You can build wheels if you just take care of the manifest. And you can even export API if you use the publication library, then you don't have to care that a lot of your stuff was kind of internal and you don't want to export it. You can be explicit about what you export and do export by explicit export instead of export everything by default. So why? Why do all of that? Because I think of code as successive approximation. We're never ever done. Using the REPL as your IDE, it's not great. It's getting better, but it does mean that you can keep working with your code in the same, leaving the environment that your code lives in. And this is not a new idea. I talked to you about my childhood, but if I was older, right, if I was like 10 or 15 years older, my childhood would have been Lisp and Smalltalk instead of Logo and Basic, and these had the same idea. You are in your environment. You're not running code, you're inside the code, and you keep running little snippets. So I want to bring back that proud tradition, literally from before I was born, and have people think that programming is more fun than it is. Thank you all. You've been a great audience.
Great. Thanks, Moshe. Thank you. Thank you, Moshe.
Sorry, I went a bit over.
It happens. Last year we ran half an hour over, so you know, we're still doing better. Here is our wonderful design in Petaluma Camelback water bottle for you. Everybody please thank Moshe Zadka again. Before our next talk, we have Samai.